Pneumatics are commonly used on a lot of FRC robots, so it's important to know how to CAD your pneumatic system, especially creating an assembly with a piston. So to create a piston assembly, first the piston has to be downloaded from bimba.com. Head over to Pneumatic, and under Actuators, go to Round Line, and depending on what kind of piston you need, whether the rod would be circular or square, you would choose either original line for circular pistons or non-rotating for pistons with a square shaft, which would mean that the shaft cannot rotate. Let's go ahead and, for this tutorial, select an original line Bimba piston. So when you get to the page and you scroll down, you'll notice that you have a little window here where you can customize your piston and generate a 3D model. Let's go ahead and generate a model, and you'll see that our piston shows up, and it even has some dimensions. I'm going to go ahead now and explain some of the dimensions and options on this window. Bore size is the diameter of the inner part of the piston. So you'll notice if I increase the bore size from 5/16 of an inch to say 3 inches, you'll notice that the piston gets a lot wider. It's important to note that the bore size is not the same as the outer diameter of the piston, which is why this is not 3 inches but it's 3.13 inches, because the bore size represents an inner diameter. Now stroke size is basically the distance the shaft will extend. So if I change this to, let's say, 10 inches, that means that the shaft will expand by 10 inches. Now if I regenerate our 3D model, you'll notice that by increasing the stroke size, the piston gets longer. Again, an important thing to notice is that this dimension provided right here is not the same thing as stroke size. That's why it is greater than the stroke size of 10 inches, because the stroke size is not the length of the piston, it's actually the distance that this shaft will extend. So this shaft will extend 10 inches. Finally, a lot of these other options are just mounting options and additions to the piston. The only addition that I would really use from Bimba would be to add a piston rod clevis, which is a little accessory that goes on the end of the shaft so that you can mount the end of the piston to another part of your mechanism. Also, in some cases, you might want a mounting bracket and a mounting nut. The mounting bracket is a little addition to the end of the piston right here that allows you to mount the piston onto another part of your mechanism with a bracket with some screw holes. And a mounting nut is this nut here, which would allow you to put the piston through a hole and then secure it by screwing on the nut. Though those are completely up to the use of your piston and how you're really going to mount the piston. In addition, some pistons, instead of having an end that looks like that, if you head up to mounting style and change it from standard front nose to universal double end or rear pivot, a lot of pistons you'll see in FRC will have the mounting style at the end look like that, so that your piston can be mounted differently with this hole in the back. Once your piston is completely configured, head over from 3D Preview to Download, and under Generate 2D, 3D CAD or Graphic File, select the drop-down and select Inventor, and select the version that is closest to your version that you're using. And then after that is selected, click Generate File, and then download the created zip file. And if you enter it, you'll notice that all the parts are in there. To open the piston assembly in Inventor, I'm going to first extract the files. And then in Inventor, I'm going to go ahead and open the assembly, which is the entire piston. Once the file loads, you'll notice on the model browser that all the individual components of the piston are parts, and that they're all grounded. This is because the piston, when imported, does not have any constraints, so if I take away the grounding and I move items around, you'll notice that everything just falls apart because there are no constraints. Now when CADing our piston, we actually want two separate assemblies. One assembly for the shaft of the piston that extends, and then another assembly for the body of the piston, which houses the shaft. To do that, I'm going to go ahead and head over to where the files have been downloaded, and I'm going to make two copies of the assembly. I'm going to name one piston shaft and the other one piston body. So after that's completed, I'm going to open both assemblies, which are essentially right now just the entire assembly of pistons. And then I'm going to go ahead and start deleting the parts that don't belong in each assembly. So for the piston body, I'm going to go ahead and delete everything that belongs on the shaft. And I'll just leave everything that forms the outside part of the piston. And I'll go ahead and color it. For this one, I'm going to go with steel, brushed, stainless. And I'm going to go ahead and save the piston body. For piston shaft, the procedure is pretty similar. I'm going to delete everything that belongs on the piston body, so the outside part of the piston. And then you go ahead and color these parts as stainless brushed. And then I'm going to go ahead and save that part. Now that we have our two separate assemblies for the piston body and the piston shaft, we're going to go ahead and create a new assembly and where we'll put the two together. Now, whenever you're creating a mechanism with pistons, you always want to create the assembly of the piston. You want to assemble your pistons in the file where the entire mechanism is being assembled. This is because when you assemble the pistons and use a constraint to create the piston motion, you want that to be available within the file where your entire mechanism is being put together. This gives your mechanism some, visual realism in that the pistons can move around with your entire mechanism. Before we begin our assembly, let's go to piston body and change the visibility of this central cylinder. Right click it and uncheck the visibility box and then save it again. Go back to our assembly and we'll ground the piston body part. Once that's grounded, we can go ahead with our first constraint and we'll constrain the piston shaft to the piston body hole by lining up those. And then this makes our piston extend within the hole. Now our next constraint is going to be a mate with a maximum. You can think of a mate with a maximum as a type of mate where we give some leeway. In this case, we want to have this piston shaft move, but we don't want it to extend past the top part of the cylinder, the top part of the piston body, or the bottom part of the piston body. That means that we need a constraint that allows it to move, but still constrains it within the boundaries of these two parts. So let's go ahead and choose our constraint to be a mate, And for our first mate, we'll select these two surfaces so that they stick together. And this means that the piston shaft will not go past this bottom cylinder. Now, click the little arrows next to apply, and then check the maximum box. The maximum box is basically a specification for the amount of leeway we want for our mate. So if I put this up to 1 inch, that is a 1 inch leeway we give to our mate so that these two surfaces have to stick together, but they can deviate from each other within 1 inch. So if I click apply, you'll notice that I can move the piston away from the surface by 1 inch. Now currently it can still go through that way without obstructing the maximum, but we'll get to that part later. So how much leeway should we really be giving to this piston? Well, we want it to go as far up as possible so that this top part of the cylinder does not go past this bottom part of the cylinder. Now the measurement for that is the height of the cylinder, 1.183, and you use the height of the cylinder and subtract it from this total distance, which is 11.183. And since the height of the cylinder was 1.183, the subtraction, the difference between those two measurements, is 10 inches. If you remember when we configured our piston on bimbo.com, we used a stroke size of 10 inches, which means that this shaft, when extended fully, will travel a total of 10 inches. And it turns out stroke size is what we want our maximum leeway measurement for our mate to be. So if we go ahead and edit our mate, let's change the maximum to 10 inches, or our stroke size that we decided for our piston. And once we apply that, you'll notice our piston goes up and out like that, but doesn't go past the first top cylinder body part. Now, it can still go down and extend through the bottom part of the piston body that way. So we'll go ahead and apply another constraint. We mate this surface to that surface, and again, we'll apply another maximum, and the number for that will again be the stroke size of our piston, which is 10 inches. And after that's done, we can move our piston around, and it will never go past these parts of the piston body. So to summarize, to complete a piston assembly, you need 3 mates. 1 mate that puts the piston shaft into the hole, and then 2 maximum mates that constrain the piston within the caps of the piston body. Now finally, we can go ahead and go to piston body and change the visibility on our cylinder and save it. And then when we head back to our assembly, our piston is fully assembled and its motion is limited, so it's realistic to how far a piston can actually extend. One last thing I'd like to reiterate is that your assembly of the piston body and the piston shaft should occur in the file where you want this motion to be possible. So that means that when you're assembling an entire mechanism in one assembly file, you should assemble your piston body and shaft there instead of importing another assembly that contains both of these. Because if you do that, then this motion won't be possible. So when you're creating a mechanism file, make sure to import piston body and piston shaft and constrain them in that mechanism file so that you can get this motion. And this will help you a lot when you're testing and refining your mechanisms, because the ability to have this piston extend will help you a lot in designing the dimensions and specifications for your. I'm now going to be going over some more advanced constraints. I previously defined a mate as sticking 2 surfaces together. So for instance, if I want this red surface to stick to this red surface, I would select 2 of them, and a mate would make them stick together. There's also another way to think about a mate. If you think about a mate as involving two geometric figures and having them coincide, you can do a lot more things. So, going back to our simple mate, imagine a plane running along the surface, the red surface of this block, and a plane running along the red surface of this block. By doing a mate, I'm taking that surface's plane and this surface's plane and having them coincide. Thinking about a mate as two geometric figures coinciding, that's a lot more types of constraints make sense. So, for instance, if I select the line of this block and also select the line of this block and I have them mate, you can imagine that the lines will coincide which would result in a hinge constraint where the lines are always coinciding. And that's why when we constrain a object into a hole, when we select the central axis, we're creating a line. And when we select the central axis of the hole, we're also creating a line. And by mating the two, we're having those lines coincide, which is why the alignment occurs where the object fits into the hole. Thinking about a mate in this more geometric sense helps you visualize a lot more types of constraints that you can do. So for instance, if I wanted this Lexan plate to attach to this piece of stock, but in a way that simulated a hinge connecting the two, I could do a mate with the bottom edge of this Lexan plate and then the top edge of this stock. And after I click apply, that would create this hinge constraint. And then if I just flush this with a 1-inch offset, then we have a Lexan plate that acts as a little flap. In addition, let's say that I wanted to constrain this whole block assembly a certain distance away from this piece of stock. I could constrain the entire VersaBlock setup to this hole. We could also do another mate, where my first selection would be the axle of this hex shaft, the central axis. My second selection would be this surface. And once a mate is applied, you see that the line coincides with the surface. That's why there's a mate, they're sticking together. The line is coinciding with the plane on the surface. And then applying an offset of, say, 4 inches, I can separate the line from the surface by a set amount. Now let's talk about flush in a new way. We previously defined flush as kind of taping two surfaces together so that they line up. You can also think about flush as an interaction of geometric figures, as we did with mate. Imagine these two surfaces have a plane that runs along them. Now, when I flush them, those two surfaces become parallel. And depending on the offset I apply, they're parallel at a certain distance. So that's maybe 1 inch, 2 inch, but you'll notice that no matter how much the offset is, the surfaces always remain parallel. Thinking about flush in this more geometric way, where it's creating two planes and making them parallel, we can find a way to align this hatch arm up with this piece of stock. So if we go ahead and head to constraint, and we select flush, and we select this surface, and select this surface, we want to make them parallel, and usually we could use an offset if we know the distance we want them to be separated, but since we don't, we can just apply a maximum, which you'll remember gives leeway, and it turns out that we actually don't need to specify a dimension for the maximum. so we can just click apply, but I'd like to repeat that since we're using flush, we're making this surface parallel with this surface, and the maximum just allows us to make them parallel at any distance that's necessary. So if you click apply, you'll notice that this remains aligned with the stock. And let's say that we don't want it to be aligned so that we can move it around. We can go ahead to the model browser, click on the constraint, right click it, and then click suppress, which temporarily disables it. And we can move our arm around, and let's say for aesthetic purposes, we want to move it back, just unsuppress the constraint and your arm will realign again. Now I'm going to talk about creating belt and pulley and chain and sprocket assemblies. Whenever you're creating a system of chain and sprockets or belt and pulleys, you always want to make sure that the pulleys and the sprockets are lined up so that a chain would or a belt would connect them with the minimum distance. So usually you accomplish that by flushing the edges of the surfaces. So in this case, if I want these two pulleys to be connected by a belt, I'd flush their surfaces so that they line up. Now, in some cases, it may not be possible because of geometric constraints. In that case, just try to get them as lined up as possible. You'll notice here, if I go ahead and measure the distance, and you'll notice that it's not perfectly lined up because we have we have 4/1000ths of an inch across the x distance. If that's the case, that's fine. Just try to minimize it because there is some tolerance in how the belt runs along the pulley. But if possible, always use a flush constraint for pulleys and chain and sprockets. This is especially important in sprockets where there's less tolerance because the chain has to mesh on the teeth of the sprocket. So after all your pulleys or your sprockets are constrained in the right place, you want to go ahead and create So the first measurement I'm going to make when CADing my belt is to measure the distance between the pulleys. I can do that by measuring the distance between the centers of the hex shafts. Get 4.253 inches. So the belt will have to be 4.253 inches long. And next, for my measurement, I'm going to measure the diameter of the pulley, the inside diameter of this rim, which is 1.083 inches. So my pulley, my belt, will have to be about that tall to fit around the pulley. So I'm going to go ahead and create a new part. And I'm going to start off with a sketch on the XZ plane. And I'll create a center point arc with a radius of the diameter of the pulley, 1.083 inches, divided by 2, because it's a radius. Go all the way around, 180 degrees. I'll create another arc, set that to 0, and I'll have the radius be exactly the same as the other one. Go around 180 degrees. Then I'll create a dimension that separates these centers by 4.253 inches. Next, I'm going to create lines that connect these two arcs, and they should be 4.253 inches in length. Now, since the thickness of a belt is about 0.06 inches, create another center point arc that is this radius, 1.083 divided by 2, I'm going to add 0.06 inches for the thickness of the belt. I'm going to sweep that around and make another arc here. Set the angle to 0, and I'll move my radius around with the mouse until it snaps into place to have the same radius as the other arc. Sweep it around 180 degrees and make lines that connect the two arcs. And if I do a quick dimension, these should be 0.06 inches apart. Finally, we'll click Finish Sketch, and we'll use the Extrude tool. And for our selection, we'll hover our mouse between the two lines until this green filling pops up, and we'll select that. And for our extrusion, since this belt will be a 9mm belt, as all belts are either 9mm or 15mm belts, this will be a 9mm belt, so that'll be our extrusion distance. Click OK. And finally, for our color, we'll use anodized black. Finally, go ahead and save this part. And for the name, since it is a 9mm belt, the first part will be 9mm belt, and the next part will be the length of the belt, not from the rim of this curve to the rim of that curve, but the distance between the centers. And if you remember, that was 4.253 inches because that was the distance between the centers of the pulleys. So now we're going to import our belt into our assembly. And for our first constraint, we're going to constrain the central axis of this curve of the belt to the central axis of this pulley. Click Apply. For our next constraint, we're going to try to constrain the central axis of this curve of the belt to this central axis of the pulley. Notice that our belt doesn't move, and if we click Apply, we get an error. That's because the distance between this pulley and that pulley is not exactly 4.253 inches. It's a number with a lot more decimal places. And so we could adjust the length of our belt to the exact right distance and chase down all the digits, but instead we can just use a rounded number, and then when we do the mate, we can give ourselves some more leeway or tolerance by adding a maximum. And our tolerance will be a small number, say 0.001 inches. And after that is applied, you'll notice our belt snaps into place. Click Apply, and our belt should be in the right orientation. For belts and pulley and chain and sprocket setups, it's very difficult to get the exact right length for the chain or the belt because of, geometry makes the numbers very long and irrational. So just use a round number for your length, a rounded number for your length, then just use a constraint with a maximum to give yourself some leeway so you're not chasing all those digits. Because ultimately, when putting belts on pulleys or putting chains on sprockets, in CAD, it's mainly there for a visual, aesthetic purpose. It serves very little structural purpose. So having some tolerance is alright. Finally, the last constraint necessary is a mate. So go ahead and select the side of the belt, and then make your second selection. If you go in between the teeth of the pulley, you'll notice that this little outline pops up. Select that, and your belt should pop into place. If you want to center the belt a bit on the pulley, you can add some offset and select that, and that is a simple belt and pulley setup. The process for making a sprocket and chain assembly is very similar to making a belt and pulley assembly. One thing to note for a sprocket assembly is to have the sprockets that are connected by chains flush if possible. And you'd want to flush the flat surfaces and not the spikes. So for instance here, you can see that it is flush this surface, this flat surface, below the teeth of the sprocket are flush with the flat surface of this sprocket. So, next thing to do to make our assembly is to measure the distance between two sprockets that will be connected. So, let's say this sprocket, and if I want the distance to this sprocket, I'll just select that, and I get about 10 inches. Like I said, with the belt and pulley assembly, we can round that to 10 inches, and when we do our constraints, we can just add some tolerance. Next, let's open up this sprocket, and we'll take some measurements for the diameter we need for our chain. So the inner diameter can be about 0.6 inches. Outer diameter can be about 0.7 inches. So let's go ahead and create a new part. Start with a 2D sketch on the YZ plane. And then we'll create a center point arc. Give it a radius of 0.6 inches. We'll then create another arc, same radius. And then we can dimension the two to be 10 inches apart. Now we'll go ahead and create another arc, this time 0.7 inches in radius. We're going to create two lines that connect those, two sets of arcs. They should be 10 inches long. Finally, we finish our sketch, extrude it, and the distance we'll extrude will be 0.3 inches for number 25 chain. We'll click OK. Finally, we'll change the appearance to iron gray, and then we'll save our part. 25 chain, and then the distance 10 inches. Now, let's place our chain in our assembly. And like we did with the belt, our first constraint will be the central axis constraint. Apply that. Now, our next constraint will be lining up this axis with the axis of the other sprocket. And of course, since the distance is not exact, we'll add a little bit of a maximum. Since that's not enough, we'll add some more. That should work. We'll click apply. And for our final constraint, we'll just have to line the chain up with the teeth of the sprocket. So we can use a flush constraint. We can center it a bit by applying a bit of an offset. It doesn't have to be exact, but that should be good. And there we have our chain assembly, chain and sprocket. So for all these, you just keep on doing it over and over again, but you can mainly use the same chain if the distance is right. Now this was with 25 chain. Since there are many different types of sprockets, and there's also 35 chain. When working with 35 chain, instead of extruding your chain by 0.3 inches, you might have to extrude it a bit more. According to Vex, you might have to extrude it by about 0.45 inches should do the job. And of course, the inner loop, the arc you make for your chain, will change depending on the sprocket you're using. An important CAD technique to have is controlling the orientation of your assembly. A good orientation is to have for an assembly is that when I click the home button, the important parts of the assembly are in view, and it's oriented normally as it closely would be in real life. This elevator-like assembly currently is on its side, and in real life it should be standing straight up. So we're going to go ahead and fix that, and also it's not even grounded. So let's start by, in your model browser, expanding the origin and then selecting the 3 planes and making them visible. Next, we're going to go ahead and constrain this bottom of the elevator to the XZ plane. Now click apply, and if necessary, we can add some more constraints, though currently it's not really necessary. But say if your assembly was angled for some reason, you'd also want to make another constraint to another plane. Now after all that's done, go ahead and hide the planes and click the home button, and your assembly should be oriented correctly after you're homing your view. And then next, go to your relationships and delete those constraints that you just made. So all the constraints you made with the planes, delete them. And then if you've done your assembly correctly and everything is constrained and its motion is limited, when one item is grounded, nothing should be able to move out of place. So to summarize, always when you click the home button, have your assembly oriented so that homing your view gives an appropriate view of the entire assembly. Second, if the orientation is off, constrain your assembly to the appropriate planes, make as many constraints as necessary, those constraints, and then ground one part of the assembly. And if the assembly is constrained correctly, nothing should fall apart.